So state space is the queues for each type, right? So okay, so the state is the queue length of each type, right? So what are transitions? You can either have an arrival and you don't do any match, in which case just one queue grows by +1, which is the type of with the probability of the arrival type. But if you also do a match, then you'll have one queue stays the same and a bunch of queues decrease by one. So that would be the transition. It will depend on your action, and we can maybe discuss offline. Well, I don't know how. So this is, I mean, yeah. So I'm not even assuming there's an adversary. Things are just IID stochastic, right? I don't know the arrival from distribution, but yeah, there's no adversary. But yeah, in that case, of course, there might be some role of random.
Sir Varun again.
So what this is the pointer. Okay, that's this one. I'll try to avoid the land between these numbers so that also the okay. So is it better if I move the slide? No, no, it's not getting issues with it. It's not moving. Okay, okay. The large. So we can wait here. Okay, sure. I'll leave that to you, decision to you.
We have 3 more minutes before the next one starts. Yeah. So
Tomorrow. Yeah. This part of it, yeah. At through it. No, this is like I think yeah. So he was just this is during his transition from Google to Adobe. Yeah, most of it will actually be like the first work. I'll just mention the results with some results right towards the end, depending on how much. Yeah. Yeah, these Wi-Fi things sometimes are a bit. So I think those old, like those standard like connectors are better. You just kind of yeah, they are reliant on like the signal being like. So if you don't like change the slide for quite some time, you have to sort of wake it up.
setting to make it not
I mean, I think it's easier solution is like those, it's like that HDMI thing, but I'm not going to experiment at this point. Yeah. Yeah. Give me 1 second. This.
Ready when you are.
Hello, everyone. Welcome back. We have another great session with Professor Siddharth Barman from IISc. He'll be talking about collective welfare as a metric in algorithmic decision making. Yeah, over to you.
Okay. So let me start by thanking the organizers for this invitation and Ashoka University for generously hosting this workshop. I'll talk about two joint works. The first one, they're sort of quite related. The first one is a paper with Arnab Mehti and Arindam Khan, and the second work, which I'll only sort of refer to very quickly towards the end, is a paper with Samrita Pral and Ayush Savarni. Let me start with the big picture first before zooming into technical details. And the point, like the big high level takeaway I want to convey, like the meta picture, is that in current times and in many, many contexts, it's important to look at algorithms as economic policies. The same way a taxation policy impacts large sections of society, it really induces welfare. Analogously, algorithmic tools, AI methods, machine learning models impact welfare very directly and sometimes in subtle manners, large sections of society. The same way as you want regulatory policies to have predictable, positive welfare outcomes and not be gamed, it's exactly the same way you want these deployed AI methods deployed in the wild to have predictable outcomes, not be gamed, and actually lead to the desired consequence, lead to the designed consequence that you had. The same way that you have to evaluate large economic policies in very uncertain environments and have them transparent, it's exactly the same way that you want these algorithmic tools, AI methods, to have predictable and explainable outcomes. So starting from normative design points to predictability to deployment across. So yeah, so I'll just give you very, so in like few minutes, I'll be very, very specific, but here I am intentionally being broad. So I'll give you like one sort of starting point is like the more classic sort of interface of computer science and game theory, things like mechanisms that have now are sort of a mature area. There are 20 years of solid work on this interface, algorithmic game theory, algorithmic mechanism design, and there have been important success stories. Things like sponsored search auctions, that's ad auctions, they're fairly an important source of monetary revenue for large corporations. And this is something where you looked at an algorithm, realized that you have private informations, you have agents with incentives, their own interests, and you want to not just design input-output algorithms, but you want to design economic mechanisms that are, say, strategy proof, truthful, and hence have this element of predictability. But what I want to be like emphasize is that the perspective, the program I'm pointing out is much more broader. It goes beyond mechanism design. So it's multifaceted. And a second more important facet that's sort of receiving a lot of attention these days is this idea of come up. This is idea of looking at fairness and welfare for algorithms that are making decisions. So just to answer the question and anchor the conversation, think of an algorithm that's making loan decisions. And now there it is literally impacting the reward, the monetary reward, the amount of loan awarded. And hence like a policy, it's inducing welfare or taking away welfare from a section of society. Algorithms or methods used to, say, shortlist CVs for job applications or methods used for deciding college admissions. These are all algorithms that are acting as policies, and hence normative considerations of fairness and welfare are quite important. So here again, you do need to have these things baked in by design and not do like post facto adjustment. So this again is a feature that's quite common in like social choice, welfare economics, having axiomatic, justified, well understood normative properties included in your policy and hence now in these tools and algorithms by design. And this will be the focus of our talk. Though again, just to sort of re-emphasize the fact that the grand perspective I'm starting out with has other elements. For instance, you do want explainability. I know it's a loaded word in the current context, but think of things like it, the kind of lessons that have been learned in welfare economics. You want taxation policies, or like the ability to file taxes, are much more transparent. You want it to be such that the actual taxes that you accrue, the government accrues, increases, and so on. So the similar sort of understanding and insights have to be carried over. It's a bridge that I'm saying does exist between econ and computer science, and it goes beyond what has been studied extensively in mechanism design. All of these are rich threads of work. My focus will be the second bullet point, which I will want to look at welfare. And as I said, one anchoring application is to say, think of loan application settings where the algorithm is assigning loans, so inducing welfare in a population of agents. But I do want you to be imaginative. Like the results are general. I am going to talk about a nice clean model. So don't, even when I say welfare, I do want you to sort of step out of the box of monetary welfare and think of things like course admission, where welfare means like opportunity, so on and so forth. It's a very clean model. So in a few slides, you'll have a very well specified technical problem in your hand, but I do want you to appreciate where the formulation is coming from. Okay, so as I said, this will be my focus. I'm looking at algorithms that are making decisions. In particular, I'll be looking at a bandit setting, and welfare is going to be my lens. I want to introduce, by design, I want a normative like anchor to bandit algorithms. So, and as I said, like the context that you should keep in mind are these algorithms that are making decisions, that are inducing rewards, loan applications, course admissions, even like scheduling things, pricing, airline pricing, so on and so forth. These all fall under the purview of what I'm going to talk about. A bit more style, like the problem is much more technical and fixed. Nonetheless, these are all grand motivating settings. What I do want to criticize right at the beginning, and if you sort of notice back, you'll sort of realize it very quickly, that in many cases, in a vast majority of machine learning algorithms, the underlying metrics are actually arithmetic means. So think of accuracy, think of regret. Regret is something that's going to be the central focus of this talk. Think of precision, recall. These are all arithmetic means. And my point to you is that there are many ways of combining numbers. Why always take the sum and divide? Like, why always the average? And average, when you sort of look at it in a economic context, like really stands out as a thumb sore. If I want to assess the income of, or the income inequality, and I look at the average, you'll very quickly criticize me. You'll say that there could be a very rich individual, could be all of the others would be poor. Measuring income by looking at averages, or measuring income inequality by looking at averages, is not a great metric. But in sharp contrast, we do that quite often without much thought when it comes to like algorithm design, or when it comes to even sacrosanct metrics like regret. So that's the critique I want to stand out with, and I really want to sort of say it. If your problem at hand is really sort of an engineering one, a utilitarian one, then great. Those standard metrics are important and they'll do the job. But what I am looking for is to sort of extend this literature to algorithms that are making decisions in welfare context. So I do want to revisit these metrics. So as I said, the generic goal is to develop metrics for these algorithms, like revisit in particular regret, and revisit it with a collective welfare lens, with a lens armed with a lot of good work that has happened in social choice, welfare economics, mathematical economics. So stand on the shoulders of those giants and sort of revisit our loved and well understood metrics for bandits in particular. So the talk will have two parts. It will be self-contained. I'll talk about one sort of notion of welfare called Nash social welfare. It has been mentioned a couple of times yesterday in a couple of talks. I'll still nonetheless tell you what it is again. And the Okay. Sorry about that. No, no, no. Excellent. So as I was saying, there are two parts to this talk, and I'll sort of do it separately. The first part is, or at least two parts to this introduction. The first part is about a welfare function, Nash social welfare, and define what that is. This comes from math econ. The second part of the talk is the regret. Again, both of these topics, interestingly, have been discussed. What I'm going to do is sort of cover them and then bring them together. Once I lay the conceptual ground, the mathematical exercise is rather simple. It's just a switch from a arithmetic mean to a geometric mean. Nonetheless, it's important to understand why am I doing it, why this sort of change in definition, change in metric. So let me do them separately and then merge. Okay, and again, just keep this at the back of the mind. What I'm going to do is like look at bandit algorithm performance with Nash social welfare. The terms in this statement, if you're not already familiar with it, will be clear in just a few slides. And the main result, again, not to sort of delay the punchline, is that even with this harder notion of regret, a more challenging version of regret, what I will get are tight bounds that actually match the the simpler, more standard notion of regret, things that have again been looked at in multiple previous talks. So what is Nash social welfare, or in particular, what is any welfare function? So very briefly and sort of at a very high level, a welfare function is nothing but a function that looks at the valuations of a population of agents. So imagine a setting where you have a T agents, T entities, T individuals. Each of them has a value Vi, and this could be induced either by a decision of an algorithm. It could be induced by, say, a resource allocation. So I have some resource, I partition it. It could be induced by some, say, taxation policy or some reward policy. So you have T individuals, T agents. Everyone has a value V1 through Vt. What a welfare function does is nothing but it tries to quantify the quality of this tuple, this T-dimensional value vector, by assigning a single number to it. So according to the welfare function, higher this resulting value, the better is your value tuple. As I said, I mean, I sort of said at that level of generality, it's just a function that it takes in this T value tuple and spits out a single number to assess the quality of the tuple. And do note that these values could have been through many ways. I mean, that's sort of that's taken away. And you say that your decision or your allocation or your algorithm is better if this welfare is higher. So higher the welfare, better is the quality of your tuple. And one very standard welfare function, I mean, is the social welfare. Right? This is the standard metric we use in most of our design objectives. Accuracy, for example, looks at a classifier and says that how is it performing over data points. Let's take the average or the weighted average. Similarly, many objectives in algorithm design always look at sum of values or sums things up. So this is social welfare. It's a very utilitarian metric. But as I've already critiqued, it's not necessary that this is the best way to assess the quality of a distribution of values, because one of them could be very high, others could be very low, rather an unfair distribution, and still the arithmetic mean, the average across these T could be high. The other extreme, which is like the fairness extreme, is what is called egalitarian welfare, and what it does also sometimes referred to as the Rawlsian welfare, where you assess the quality of a valuation tuple by looking at the minimum value across all these things. So you say that one distribution or one decision is better than the other if the poorest individual is better off in the second one than the former. So you're looking at the min across these three. What I am actually going to do is a great balance between these two extremes, which is the geometric mean of the values. So I'm sitting right in between. In particular, by the AMGM inequality, what I have is that the geometric mean is at most the arithmetic mean, so it's less than that. It's a mean, so it's at least the min value. So it strikes a beautiful balance between the utilitarian extreme and the egalitarian extreme. And this is called Nash social welfare. This would be the protagonist of my talk. This would be the welfare function that I'm going to work with. I am looking at the average of the logs, but that does change a lot of things. In a minute, I'll tell you like a big distinction, important distinction between the arithmetic mean and this one. So yeah, it would be different. That's risk adjusted. This is more like I'm looking at the arithmetic mean of the log of the value. So if I take the log of geometric mean, I get 1 over t some log. So it's more. That's a better idea for very sort of useful reasons. And here are the reasons. So this is not an exercise in aesthetics, however much I like the geometric mean. The reason for the reason why welfare economists, social choice theorists have liked, or in fact identified this welfare metric, is because it actually comes with an axiomatic basis. So the exercise that is done in that field is that you start with a set of principles, a set of axioms, and then you try to say, oh, what are the welfare functions that satisfy these fairness and welfare axioms? One important one being the Pigot-Dalton principle, which is very roughly speaking saying that if you do Robin Hood operations, take epsilon value from a rich person, give epsilon, the welfare function should strictly improve. So that's a axiom, that's a property that Nash welfare satisfies. And another important one is scale freeness. Notice that the geometric mean does not depend on the scale of the valuation. So an individual can report its value in rupees, yen, or dollars. Because it's a geometric mean, more formally, I can look at an agent's value, scale it multiplicatively, and that factor will just pop out. In contrast, if I look at social welfare, if one of the individuals starts reporting its value with a scaling factor, let's say multiplies everything by 1,000, you'll start giving everything to that individual. So that scale freeness is involved in Nash welfare. It is not involved in, say, social welfare. And in fact, there is this set of key axioms. And what one can show, interestingly, is that if you start with these key axioms, these key properties, up to affine translations, the geometric mean, i.e. the Nash welfare, is the unique welfare function that satisfies it. So in the world, as I said, the exercise here is that you start with properties and then try to find a welfare function that satisfies it. And like this is an exercise that's done by welfare economists, has been done extensively. Books have been written on this. The thing that comes out axiomatically is. So Nash studied this again with an axiomatic underpinning in the bargaining context. Yeah, so the solution to Nash bargaining, the bargaining problem is this geometric mean, and hence its sort of namesake after that. Yeah. Important welfare function sort of, again, strikes a balance between utilitarian and egalitarian extremes. This is going to be focus of my talk. And just to sort of sum things up with a simple example, imagine a setting, why is it a fair welfare function to look at? So imagine a setting where I have T agents, again, those, and in the first setting, half of the agents are getting a value of 0, the remaining T by 2 are getting a value of half, whereas in the other valuation tuple, everyone is getting a value, all the T agents are getting a value of 1/4. Social welfare remains unchanged. I mean, both the arithmetic mean is just 1/4, but if you look at the geometric mean, the left one is 0, because there's a 0, it kills the product. The Nash welfare does focus more balanced, more equitable value distributions. So it really does prefer valuations that are more, but at the same time, axiomatically, fairness is baked in it it does prefer evaluations that are more balanced. So that's it. Like that's my motivation for looking at Nash welfare. The summary is that I will focus on geometric mean as a good performance metric. Okay, so now I've finished one part, which is that I've told you what Nash welfare is. What remains to do for me is talk about regret. Again, this is something that has been done multiple times, but just so we have the same notation in hand, let me quickly also go over what is regret. In particular, I'll actually be looking at a much more basic setting, the stochastic multi-armed bandit setting, so a cleaner thing. So once I've described to you this other element of regret, which is now coming from online learning literature, I'll sort of combine the two and I'll sort of realize the goal that I had set out for myself. Okay, so bandit literature, again, extensively well studied. This is sort of workshop dedicated to it. There are books written on it, conferences. Every month there are lots and lots of work, multiple posters on it right outside the hall. Extremely well studied setup. And what it does is it gives me a formal framework to talk about sequential decision making under uncertainty. I'll make this very clear, but just want you to say that like what you're going to see is like not even a tip of the iceberg. There's a huge body of literature on bandit, on these sort of regret minimization, in online learning, in reinforcement learning, and even in game theory. So here's the formalism I'm going to work with. So imagine that you have an algorithm, a decision maker, and it has to make sequential decisions in the following environment. That the algorithm, the decision maker, has access to k distributions. These distributions are referred to as arms. Comes from this slot machine analogy. So you have these k distributions. Notably, however, you do not a priori know the statistical properties of this distribution. So what you have are these k distributions sitting in front of you, but you do not know what are the means, for example, or the variances of these distributions. What you can do, or what the algorithm can do, is pick one of these distributions and then draw a reward from it, and it will get an independent draw from that. So the algorithm can say, okay, let me look at distribution 3 and just draw a sample from it, and that's the reward you get. It can go back to distribution 3 and get an independent reward drawn again from the same distribution, or it can choose to move on to a different distribution. These distributions are, I'm going to keep referring to them as arms. And the algorithm can do this for t rounds sequentially. What is the goal of the algorithm? The goal of the algorithm, roughly speaking, is to accrue large reward, like pick those draws such that it gets high rewards. So in every round t, say, the algorithm selects some arm. I'll use this, it's not a notationally heavy talk, but this IT is going to be very important. In round t, it picks one of these k distributions, and IT is the index of that. So if IT is 1, it means that in round small t, you pick the first distribution. If IT is 2, it means you pick the second distribution. And once you make the choice of your distribution, you get a reward from that distribution. So you have k choices. IT specifies what choice you make in round small t, and t ranges from 1 to t, capital T sequentially. Okay. And you receive, as I said multiple times now, you do receive an arm-specific reward. And this is the expected value. If IT is a random variable, then this is the reward that you're expecting. This is the ex ante reward for you in round t. Okay, but if towards a benchmark, so this is a hypothetical because, I mean, the algorithm does not know the means, the statistical properties of the distributions, but just to set an ideal, like a benchmark to aim for, if the algorithm knew the means of these distributions, what it could have done was pick the distribution with the largest mean and just every time draw from it. So every time it would get a reward, which is mu star in expectation. So if mu1, mu2, mu k are the means of these distributions, you could have, if you had this knowledge, which you don't, you could have picked the best distribution in terms of the mean, always in all the capital T rounds, drawn the reward from it, and mu star would be your average reward. However, this you don't know, and you want to understand how close can you get to this mu star, and this is where the very well studied notion of regret comes in. It quantifies this difference. It says that the benchmark, ex ante benchmark is mu star. The expected value of mu it is the reward you're getting in round t. They're capital T such rounds. You look at the arithmetic mean, and this is the difference you're trying to minimize. So regret is an objective which you always try to minimize. Many algorithms, I mean, beautiful work has gone into a lot of extensions, a lot of analytic, algorithmic ideas that aim for regret minimization. It's a career onto itself, regret minimization, I mean, both in life and in academics. So this is the metric that's extremely well studied. And right here, let me point out that there's an arithmetic mean sitting there. And not just to even rub salt in this observation, let me give you two very classic applications that should make you a little uncomfortable if you have already worked on this metric a lot. The first one actually goes back to Thomson in 1933. It's a fundamental paper that sets, like, in fact, is cited as the classic work in bandit literature, and it's drug trials. So what is the setting here? It's slightly stylized, but it maps exactly to this formal framework. You have K drugs, and you do not upfront know the efficacy of these drugs. So these K drugs are your K arms, they are the K distributions, and you have a population of T agents, capital T agents, that arrive sequentially. When a person arrives, you pick one of these drugs, give it to the person, one of these K drugs, see if it works or not. So realize a draw from the distribution. So if you were to give the ith drug, that corresponds to like drawing from the ith distribution. And again, if you're looking at regret, what you're saying is, had I known the best drug in hindsight, which you don't, mu star would have been my average efficacy, versus I'm now looking at the social welfare induced across the population, where this E mu t is the expected efficacy of individual T. So every T is an individual. I have a population of capital T agents, and what I am looking at, the performance metric is capturing, is trying to maximize social welfare. It's trying to maximize this quantity by minimizing this difference. Of course, there's an issue here. Like, if I want to look at it from a welfare or fairness perspective, you can, I mean, some standard algorithms do, treat the initial part of the population as lab rats, right? Get a very bad efficacy on them, but then do really well for most of the tail population. And the social welfare will not capture it, because the efficacy for a vast majority is good. Even if you sacrifice a small initial segment, you are good to go. The regret can be very low, even if you are very unfair to an initial part of the application. Let me give you another one, used a lot, commercially very important application, display ads. So a lot of online companies use bandit algorithms to decide what are called ad slots or slates. When a user comes in, they decide the configuration of where the organic component of, say, a search result sits versus how the ads are displayed, how many ads, so on and so forth. And so these possible configurations in this now are the K distributions. The user engagement is the reward. And when you're trying to minimize regret, what you're saying is that on average, the social welfare should be high. And as you explore which is a better or which is a good configuration to show. So both these applications are, chosen by me to highlight the welfare need of this context. And now that I have this, let me also mention that I've been saying it a lot, but let me quantify this. Has been studied extensively. This is over a 20-year-old algorithm by Euler that achieves a regret. This, i.e., it's a decision-making algorithm that judiciously picks arms such that this metric drops as this particular function. So notice that as a t increases, capital T increases, this expression goes to 0. It goes to 0 as 1 over square root t, and it has a square root dependence also on the number of arms. So it's a very well studied algorithm. Up to log factors, it's tight. And I will very quickly at least tell you what the algorithm does. So I will go into some details of the algorithm, but this is a very well-known result. And as I said, it's tight in the sense that there are known lower bounds. Let's say that up to log factors, you cannot do better than this in terms of the standard regret notion that I've written on the slide. Okay, so at least in terms of the conceptual pillars we are set, I've told you what Nash welfare is from MathEcon, told you what regret is from online learning, and now I am able to execute my vision. I am able to tell you how do I quantify regret looking at a welfarist perspective. Exercise is extremely simple. It's just one switch. This is standard regret, mu star minus social welfare. This is Nash regret. This is the notion we define. We are now looking at fairness or welfare across time. I have T individuals. For every individual, this expected reward ex ante is the value I associate with every individual capital T. And instead of evaluating the social welfare of the population, I'm evaluating their Nash social welfare. And I'm saying that, oh, let me try to minimize this quantity. Do notice I have not made life easy for myself technically. What the AMGM inequality tells me is that if I do achieve an upper bound, any upper bound of Nash regret, that actually applies to standard regret. Right? So I have picked for myself a harder objective. And a priori, I mean, even when we started the project, it wasn't clear to us if we can get bounds that are commensurate with, let's say, UCB, or let alone achieve the lower bounds known for standard regret. But with these two notions, as I said, Euler achieves this bound, and the punchline, which I'll try to sort of convey at least some of the technical insights, is that in fact you can achieve up to constants. In fact, like it's not even logarithmic, up to constant. We have an algorithm that achieves Nash regret exactly the same as Euler's algorithm for. There's a log T that O tilde I'm hiding some sin. So it's not the I'm not writing it as like T mu star minus the sum of rewards. I'm averaging it out. So it's mu star minus. So it's this, there's an 1 over T here, which brings this to 1 over square. Yeah, in the instance base, I'm not doing instance base, yeah. I could, it's a good question to look at, yeah. Yeah. Yeah, so I'm assuming, well, okay, one of them can have zero mean, and I'll actually bypass that issue. But it's exactly the same set of assumptions that you have for UCB. I'm not going to make any, there's no sin I'm hiding here. So the exact same setup, like say, mu i's are between 0, 1, they can be 0. So even that pathology we take care of. I'll show, like when I get to it, I'll point you how. But exactly for the same setup, so like if you're looking, yeah, so no more like hidden assumptions. Yeah. Exactly. So this is an important point. It's a technical point, but the expectation sits inside the geometric mean, not outside. So I could, in principle, always randomize, always pick one. So even if one arm has non-zero, with probability 1 over k, I'll pick that. So this expected value would be low. It would be like 1 over k. But nonetheless, it's non-zero. So that's one way to get non-zero. But again, if you do that for many, many rounds, geometric mean gets great. So the point is, you can say by just complete, like uniformly at random picking arms, avoid that pathology. You have to be careful that you can't do it for extended period of time, right? For many, many rounds. Yeah, it comes up in the, it'll come up and point at you again. Yeah. Yeah, 0. Because I mean, let's say the first term is exactly the same case. Let's say mu1 is 0. Your UCB in the first, like, does a round robin for k rounds. It always picks the first arm. I mean, I think, yeah, if you do additive shifts, you at least can avoid that, but it's not clear. In fact, like if you slightly go more general, like linear bandits, which I do at the end, you can come up with examples that even things like Thompson sampling and standard UCB for like some standard data set do fail. So there was, yeah, it's not, I mean, yeah, UCB in general, yeah, exactly. So, and this is intentional. I want Nash social welfare says I don't want some people to be very poor and then just worry about that. So the geometric mean is intentionally doing that. Yes and no. So I mean, there's a small, very yes. So I mean, there's some sort of a trade-off there, but yeah, it's I mean, let me just say this way: a standard like instantiation of UCB, we have tried both empirically and through examples. It doesn't. There's a necessity to change the algorithm, and thankfully, it's not a. I mean, it's a very subtle change, but I'll try to convey why that's interesting. Yes. Just log. Just log. Yeah. It's actually the you whatever regret bound you have for UCB, you multiply by 4, you get R. No. Yeah. I mean, just for cleanliness, I wrote it, but it's literally a factor of 4 or 6, something like that. Yeah. So every time slot is an individual, and that's the connect. Those are the applications. So like drug trials, yes. So capital T agents and capital T time steps. That's the intentional thing. So both display ads and drug. This was and I very cunningly chose those applications. Yeah. Okay. So that's the result. Again, as I said, this is joint work with Arindam and Arnab. And so let me just quickly, how much time do I have? Okay, so let me quickly tell you what UCB does, and I'll not have time for like proof details, but I'll be able to at least tell you like one like light bulb that forces the change in sort of, yeah, I'll be happy to talk about proof details going forward. So this is the standard upper confidence bound algorithm that of Hoyer, 20 years old. There may multiple other algorithms, like as was pointed out there, ones that do instance specific optimal regret bounds. This is an instance independent one. It's a function of capital T. And what it does is it sort of proceeds again sequentially. At any point, for any arm I, it looks at how many times has this arm already been sampled. So let's say Ni is that number. So looking at, let's say, arm 7, and you say that, and you're in round 20, you say that, okay, how many times in the past 19 rounds have I sampled this arm 7? So let's say that's Ni, and I'll compute the empirical mean of this arm in the history, in the past 19 rounds. Let me call that mu hat I. So a very instinctive thing to do is to pull the arm which has the highest empirical mean, mu hat I. So because this is the arm that has so far yielded the highest reward. What you do is you actually add a confidence term to it. Intuitively, it's to account for the fact that you should favor arms that have small ni, that have been sampled fewer times so far. So this is the confidence term width that you arm to attach to every arm I, and then pick the arm which has the highest UCB value, upper confidence bound value. Here's it pictorially. So this x-axis represents all the k distributions, k arms I have. At any point of time, you compute these numbers, UCVIs for all the arms, and then not look at the highest empirical mean, which say in this picture is the second arm, but you actually look at the arm with the highest UCB value, play that. So for that arm, your Ni now increments, you update the parameters. For the other arms, the UCB values stay as is. So you sort of update these numbers for every arm and greedily just do that over and over again. And this gives you the UCB algorithm. So every time the arm that you select is the one highest UCB, rinse, repeat, update the parameters. Okay, and what I want you to sort of notice is that I mean, it's a nice analysis, and in fact, UCB itself has multiple ways of analyzing it. It's in fact sometimes very useful. And what good is a theorem if you don't know 4 proofs of it? So UCB has more than 4 proofs, but one key technical hammer that does show up in all of these analyses is Hoeffding's inequality. And what it says is that what is the difference between the empirical mean mu hat I and mu I? It's more than epsilon by this sub-Gaussian tail. And if you choose this confidence bound as your epsilon, what you do get is that this probability is less than 1 over t squared. So you can then apply union bound over the t rounds. Notice, however, this version of Hoeffding is an absolute approximation. It's saying that mu hat I is additively close to mu I if you choose this epsilon. When you're looking at arithmetic means, additive errors are completely kosher. Just separate out. When looking at geometric mean, you do realize how much you miss linearity of expectation. So it's gone. You have a geometric mean, not a sum. So now what you do need when you have geometric means at a very high level, and I'm doing a bit of injustice to the analysis, but the key insight that when you're looking at geometric means, you do need relative approximations. You want something like a Chernoff bound, if you know what that is. But what you want is that mu hat and mu I are multiplicatively close to each other. So you do need a stronger version of Hoeffding. And this is sort of the key hammer that separates this. The log, again, the issue is that if the mu i's are close to 0, the log shoots to minus infinity. It becomes unbounded. Yeah. So this is UCB. This is what it does. Let me quickly tell you what we do. The idea is similar as before. You associate a number and index with every arm. The subtle difference is that in the confidence bound, if you notice, I have a mu hat I sitting inside. So I'm actually dampened my confidence width a bit. But let me quickly just, in the interest of time, say, so what you do is do a slight warm up for a small number of rounds. You do this initial thing to just weed out things that are 0 or very close to 0. And then you run this algorithm with this NCB, the Nash confidence bound. The key point is that you do need this relative approximation version, that is mu hat and mu I are within 1 plus minus delta of each other. And with the warm start, you can show that you can do this. And this again, if you sort of carefully notice, the choice of confidence bound matters, and you still get the same sort of guarantee that across all rounds, they are going to be close to each other. So now, instead of an additive difference between mu hat and mu I, after this like warm start and some careful analysis, you can show that with this confidence bounds, you do have like a multiplicative fold between mu hat I. That, very roughly speaking, is what the algorithm does. And as I said, if you sort of do the analysis, you get that the regret bound effectively matches Euler up to, in fact, constants. And it's, no, I'm not being fair. There's no fairness to the arms. It's fairness across rounds. So I'm like yeah. So if, I mean, there are interesting papers that look at, but my applications are the ones where, like, I don't care if some drug company loses their K-drug companies. I want efficacy across the population of capital T rounds to be good. Like one simple example, and like the more elaborate ones, is that let's say the first mu1 is 0. And then if you do UCB, where in the first round you always pick mu1, you're gone. So this initial uniform like sampling sort of manages to bypass this, but you have to be careful. You only can do it for like square root t rounds and still get away with it. Yeah. So for in this case, it's just, yeah, you just look at the 3 French authors and find yourself lucky. The next result I'm about to tell you, we had to like derive a new concentration. Yeah. So this was the case for, yeah, please. Yeah, sure, I'll be done. Yeah. So it's not the best term identification problem. Yeah. Yeah, so it's part in the analysis, but also as I told you, like the regret, it's a harder regret notion than say the standard one. Yeah, yeah. So after this warm start of like square root t, you do start it's not mentioned in the result, but if you look at the analysis, that does come out. So the exact same sort of suboptimalities do hold, in fact, in some sense better. Here it is, but I mean, I'll make a comment that there's a, yeah, the doubling trick. Again, there's some subtleties, but one can, I've made a comment later on, it does work. But for now I'm assuming, yeah. Yeah. Yes, please. What is a fixed confidence? What is BAI? Oh, okay. Good. So best term, I like, no, not really. This is fairness across time. So I don't have lab rats to, like best term identification. The analogy would be I literally have lab rats and I test them out. At the end, I'll give you like a very general open problem, which will answer both your and my question in a single sweep. Yeah.
There's actually one framework. They do this like, okay, some identification with minimal regret. So
yeah,
during the thing, there's a stopping time, but after that stopping time, you want to minimize.
Yes, but at the same time, there are these results by Bubeck et al. That show that these two, like, there's a gap between simple regret and sort of average regret. Yeah. So those, I mean, there are impossibility results as well. That an algorithm that does optimally for this will be suboptimal for the other. So yeah, I think this Bubeck. I mean, yeah, offline I'll find the reference for you. Yeah. Okay, so very quickly, I'm not going to spend more time. I just want to sort of advertise the result that this does extend to the setting called linear bandits, where the optimal value, the means of every arm is a linear function of this hidden parameter theta. Okay, this hidden parameter theta, literally hidden. Okay, you'll have to help me again, Varun. I have one more minute at least. Okay, I'll try to, yeah.
Okay, we have a break after this.
I want to be on time. Yeah. What is this? It's time. Wi-Fi isn't helping. No? Right. So as I said, this is generalization of the standard stochastic multi-arm. There's a linear functional that defines the means, and every arm sort of is associated with, let's say, a known d-dimensional, let's say, feature vector x. Mu star again is the best arm with this thing. You can again define Nash regret exactly as before, the optimal minus the geometric mean of what you receive. And for here again, we do get regret guarantees that are tight up to a square root d factor. So tight in the sense that they match the standard regret. And I mean, yeah, just to sort of say here we had to sort of derive concentration bounds. It works for sub-Poisson random variables, has nice connections to what are called Kuiper-Wolfowitz optimal design, like some sort of geometric ideas, like using nice John ellipsoid kind of stuff. So in the interest of time, I'll not be able to sort of spell out, but there's some nice technical ideas that are like standalone, interesting, happy to talk about this offline. Let me just quickly end up with some sort of interesting works. I do think this is worth studying, like actually testing out Nash regret for some applications like ad, like display ads or recommendation systems. As was being asked, like is there a way to sort of connect it to best arm identification and so on? What you can do is actually look at this more general form. This is called P mean welfare, generalized mean welfare. It deceptively looks like a norm, but notice that P is not more than 1. It's in fact, this parameter P is less than equal to 1, and it's a mean. So it's 1 over T times the mean of V to the P. So P equal to 1 is arithmetic mean. P equal to minus 1 is harmonic mean. When P tends to 0, this expression in fact goes to Nash welfare. In the limit, it is the geometric mean. Useful, like, nice exercise in L'Hopital. And when P goes to minus infinity, it is the egalitarian welfare. It is the best arm identification problem. So as you change P, this thing goes from social welfare to Nash welfare to harmonic mean, which is studied in some network problems, to egalitarian. So you can actually generalize this whole spectrum by looking at this single sort of welfare function, if you will, and so defined regret accordingly. This again is a nice technical problem. There are a lot of arguments that I mentioned that are sort of tailored for Nash welfare, like the relative approximation. So getting this actually forces you to like revisit a lot of concentration bounds again. But I'll stop there, mention that as an interesting problem, and thank you for your time.
Couple of questions.
Yes, please. It won't be lower. So like, I mean, okay, this is not instance. This is like a worst case lower bound, if you will. So the lower bound for like standard regret and sort of, I mean, they are very close, like they are tight actually. The upper bound for, I am saying for Nash, it matches here, so I can't have a gap. Nash regret is a harder quantity, yeah. Yeah. So I'm not, maybe universal answer is not, like, again, this Bubek's incompatibility tells me I cannot, like for P equal to 1 to infinity. Yeah, so ranges or even P specific would be interesting to me. Yeah, for each P. Yeah. Excellent. Thanks. Please enjoy the coffee.